In this video, we'll cover the empirical assignment for Chapter 13. In problem 1, I'm going to have you duplicate column 4 of table 13.2 in the text. So I've given you the data set that was used to construct those tables. There's even a program down here that will run them for you. We'll get to that in a moment. Hopefully you've read this, but if not, let me quickly go over what the experiment was here. In Tennessee, there was a program called STAR where they wanted to see the effect of class size on test scores. So they randomly assigned students into 3 types of classes: a small class, a regular class, and a class with an aide, a permanent aide. Now normally when we've randomized so far or talked about it, it's only been into 2 categories. For instance, job training or not, or fertilize the crops or not, or something like that. And so we took that particular variable, randomized it across some sample from the population, and then applied the treatment to those that were selected randomly. And that randomization avoids the need to have any controls because all of the characteristics are randomly distributed across the population, so they cancel out in aggregate. And so all you have to include, if you want to run these differences regression, are just the randomization variable. And for us so far, that's just been X, for instance, as I said before, took the job training program or not. So far when we've run this, we've run it as yi equals beta naught plus beta 1 x plus an error, and that was the basic difference equation. And then you could see what effect the treatment had on the outcome from that. And you, as I said, you didn't need any controls as long as this variable was truly randomized in the treatment. So in this example, there's 3 categories instead of 2. There's 3 different classrooms. So in order to capture that, we need 2 dummy variables in order to capture those 3 things. So we have one dummy variable that's 1 if it's a small class and 0 otherwise, and 1 if there's a regular aide and 0 otherwise. These would never be 1 at the same time. The regular aides were only assigned to regular size classrooms. And then the ones that are left over, if you add these together, you'll get a bunch of 1s and 0s. All those other 0s represent the regular classrooms, and those are the baseline, and those are captured in the constant. Okay, now the next thing is there's a list of variables. You need the dependent variable is the test score for kindergartner, people who'd been in the program through kindergarten, or in kindergarten, sorry. And here's the small class dummy variable for kindergarten. Here's the regular class with aide dummy. And then some control variables, the experience of teachers, a dummy for boy and girl, dummy for free lunch, and so on. And so your job's just going to be to take this do file that I provided you, which duplicates column 4 of table 13.2, or table 2 of chapter 13, column 4, and instead of running it for kindergarten, which is what that table is about, run it for second graders instead. Let me pull up the program here. So this is the replication program for chapter 13. Starts off as usual, sets the delimiter, the end of the line character, clears everything out, clears the log file, starts a new log file, so on, stops it from paging, reads in the data set. This, of course, would have to be the path to the data set on your computer, just like always. This is just, in case you're interested, there was actually a bigger data set called WebStar that had a whole bunch of other variables. And what Stock and Watson did is to take that bigger data set and create another data set called star_SW. That's the one we're using. And they created a bunch of variables from that bigger data set. Not going to worry about that too much, but it tells you like the test score for kindergartens, the math score plus the reading score, and so on. So it just tells you what's in there. Okay, here's table 13.1, and we're encountering a command we haven't seen before, which is this preserve command. Let me take a look at the data for a second because it'll be easier to understand if we do that first. Excuse me. So here are the data for your problem and for the table. And you can see there's this, the name of the program was STAR, and it's indexed with either kindergarten, first, second, third grade. And this tells you whether the student was in the program in those particular grades. So this student was in all 4 years, was in the school. The program went on for that long. This student wasn't in the first 3 years, entered the 4th. This one was in the last 2 years, some that were there all the time. There's some that were entered and then left. Here's one that was just there for a year, and so on. Here's one that was in, left, and re-entered. Not sure what happened there. But anyway, so there's all sorts of experiences. We want to just run it for second grade for your empirical assignment. The book just does it for kindergarten. So what we need to do is create a new data set that just has this observation 2 where there's a yes, observation 3, observation 5, and so on, and throw away all the others. And that's what this command is going to do. So what you do is you say preserve. What that does is it saves the original data set, sets it aside and saves it. And then you say keep if the star k variable is equal to 1. Now 1 is just the same as a yes logically to the computer, to this program. And so what this will do is only keep the observations where there's a yes. And so create a new data set that's just the kindergarten observations. This one here. Then you say restore, and it puts back the original data set and throws away that temporary. So what this does is it says, okay, keep the old data set, create a new one that's just the kindergarten. Then they did some summaries, which I commented it out because I got tired of looking at those big summaries. Run a regression. This is just the basic differences equation with no controls, with robust standard errors as always. So the test score on the 2 randomization dummies for the 3 categories. This does it for first grade, third grade, and so on. Down here is where your this very last line is what produces column 4 of the table 2 that you need. So that's the one you want to duplicate, and you'll just have to change some variable names. It's pretty easy. What I need to explain, though, is this areg command. We don't want to just run on these variables. There's reasons to think, and the book explains it when it discusses it. I don't want to take the time here, but there's reasons to include fixed effects in this regression. And so what we need to do is create a dummy for every school. Now in the data set, there's a variable called school ID for kindergarten. Here's school ID for first, school ID for second, and over here is school ID for third, and so on. So there's a school ID variable. This student was in the same school the whole time. This student wasn't in the first year, at least in the schools in the sample. Then was in school 50. The numbers will repeat in places because some students are in the same school. And so, again, this is the ID for kindergarten. So here's a student in school 79. Here's another one in 79, and so on. And there's 79 different schools. So what we would need to do is create 79 different dummy variables, add them to this. So we could do that with a star variable or something like that, but we don't want to have to create all of those. So what this will do, this areg, this absorbing regression, will take the school ID variable and create 79 dummies, then as always throw one out. And so it'll put in the dummies 2 through 79 into the regression, and then we'll get a regression with fixed effects. So this is just a way of running this. Now actually, there's a little bit more to this command. Sometimes you have these huge data sets, and you might have 10, 20, 30,000 fixed effects with a data set of 1 million or something like that. That's too many variables for the program to handle. This absorbing regression is a different way of estimating that gives you the same results, where you don't actually have to include the dummy variables in the regression. In fact, it never even estimates their coefficients, but it gives you the same results. And so it's useful when you have huge numbers of dummies. And 79, I guess, was enough. We could have, as I said before, we've done this in the past. There's ways to create dummy variables and then include them, but this is another way to do it. Okay, so that's the absorbing regression. So that's all there is. So the first problem should be pretty easy for you. It's just a matter of amending this do file a little bit, and it's a fairly simple change. So you shouldn't have much trouble with that. In the second problem, I turned to a different data set and a different experiment. And this is based on empirical problem 13.1 from the textbook. And in this problem, problem 2, the experiment is to take a bunch of resumes and then randomly assign some with black sounding names, send them out, and then see what the callback rate is, and then see if there's any difference in the callback rate according to the type of name that's on the resume. And so that's the experiment. So you randomize on that name variable, on the African American sounding name variable. And so let me pull up the code for that one. Oh, we don't need this yet. Never mind. Let me pull this up. So this is over here. So this is, actually we don't need this yet. Sorry. Let me go back to the problem. So this problem is really pretty easy. The first part, I actually tell you exactly what to run. This is just the basic differences regression. So problem 2 is just, for this problem, run the basic differences regression. So you run callback, which is call underscore back in the data set on black, and that's it, because that's the randomization variable. That's the one that was used to assign the names. So this is 1 when one type of name was when the African American sounding names were used, and 0 otherwise. And so then just tell me what the results were, and then part B is just add a couple more variables to the regression, see if it makes any difference. And then finally, you do a test to make sure that this variable, we've called this X in the textbook and in the lectures, this variable black is truly randomized. And so all you have to do there's a regression that's outlined on page 480, which is fairly simple. And we talked about in lecture that you can use to test this. Okay, question 3. The regressions are pretty easy. The first thing you're going to be asked to do, or the first thing you'll need to do, is to generate an interaction variable. And so in this particular case, I called it fxb, f times b, and that's female times black. So you create this multiplicative, this what we call an interaction variable. So let's go to the code for this. Now, I'm not actually going to code this for you. I'm just going to give you an example that's very, very similar. And this is given at the very bottom here. So everything that's on the screen in a second here, these notes, is given here in a Word file. So if you need that, or if you want to take a look at it, you have it. You could even pause this and pull it up right now if you wanted. Okay. So suppose you have the following data. So I want to explain what these interaction terms can do for you. So Y is just some outcome. For your problem, it's the callback rate. I'm going to pretend like it's the wage here. And your treatment was the name variable. My treatment's going to be a job training program. You'll also have a sex dummy. Mine will be 1 if it's female and 0 otherwise. And then I have this interaction term, which is W, the female dummy, against X, which is the randomization variable. So then you just read the data in the usual way. You know how to do that now. And then, so you'll read in the data that's given to you here. And you should know how to do that by now. And then create that interaction variable. And then what you want to use it for, so why have an interaction variable? Well, suppose you want to know a question like, what's the difference in the test scores between the treated and the untreated group? Or what's the difference in the callback rate? Or what's the difference in the wage rate between the treated and the untreated group? And I can use the W variable to further separate the problem into males and females. So maybe I want to know what's the difference in the callback rate for treated and untreated men, and what's the difference in the callback rate for treated and untreated women? Or I could ask a different type of question. What's the difference in the callback rate between treated men and treated women? Or whatever the W is. So that what this W will do, if it's a dummy variable, is separate the data into two groups, and then I can ask questions about those two groups once I include this interaction term. And so let's do the treated versus untreated men. So what you do is you estimate this model in the normal way, and then you use the display command. And remember this underscore beta name of variable in Stata? That gives you the coefficient that was estimated for each of these variables. So it's the coefficient in front of the x. It's underscore beta underscore b x. And so this is just the predicted values. Wx is going to be the 0, 1. So what I did is just put in the values for treated men. So I've got the constant. So this is predicted value for treated men. And then I've got this x variable is whether they were treated or not. They were, so I set the dummy variable equal to 1. That's what that 1 is. This variable is the sex dummy. Since it's male, I set it to 0. If it was female, I'd make that 1. And then this is the interaction term W, which is 0, times x, the treatment, which is 1. And so this display command would display the outcome, the predicted outcome, for a treated male. Then for an untreated male, all I have to do is change the x variable to 0. And so I changed, here it was 1, I change it to 0 here. Up here in this equation it was 1, and I change it to 0 here. So you just change the randomization variable, dummy, from one variable to the other. And then finally you take the difference. So here's the treated male minus the untreated male result, and I get the difference, and that's what I'm after. Now, if you work that out, that difference is just this coefficient, bx. If you thought about it long enough, that would be logical, and you might try to see if you can get that intuition. But the difference is just bx. So if I want to know if this difference is statistically significant, all I have to do is look at the output for this regression and look at the t-statistic for the x variable. And it'll tell me that t-statistic is a t-statistic for this difference between the two outcomes. Now suppose that I want to know the value for women. Well, all I have to do is take the problem I just did. I'll just take the difference and just change the dummy variable for the W from 0 to 1. So I just copied this down here. It's the same difference, and the only thing I have to change is instead of having these dummies here be 0 for male, I make them 1 for female. And same thing over here in the multiplicative term. Instead of 2 zeros, I have 2 1s down here. Now, if you actually cancel all the things that cancel, those two things cancel when you subtract. Those two will cancel. This will be 0. This will be 0 because you're multiplying by 0. So you just get this term plus this term. So after canceling, what you get is the coefficient on x plus the coefficient on the interaction term. So that's what the difference is. So when you ran this regression up here, that's just this x coefficient here plus this wx coefficient is what this will display for you. And if I want to know if that's significant or not, I can use the test command. I can't just look at the output because there isn't one. There isn't a t-test on the output for that sum, but I can use the test command, so I can test x, which is the coefficient, the coefficient on the x variable plus the coefficient on the wx variable equals 0. This will actually give me an f statistic for a single restriction, if you remember that f is equal to t squared. So I just took the square root of f. Rf is the value of the f statistic from this test, and hat 0.5 takes the square root. So that'll display the t statistic, and it has the same significance level as the f. This is just a way of getting the t if you want it. I think in one of the problems I asked for the t, and it'll give you the f. Just take the square root of the f to get it. All right. You can ask other questions too, like, for instance, what's the difference for treated men and treated women? So I just take I've already estimated the equation up here, so I just do something else with the coefficients. I just take that same difference, but I put in the right values. So in this case, they're both treated, so Bx in both cases is 1. In one case, it's women. In one case, it's men. And then I make the interaction term. They're both treated, so it's 1, 1 on the right-hand side of that multiplication, and 1 and 0 here on this side. And so this will give me the difference. If you add that up, what you'll get, oops, this is an error. That should be a plus. Let me save that. If you want to test this, again, just use the test command. Up here it was the x plus wx. Here it's w plus wx. So that gives you the difference between treated men and treated women, that w plus wx. And then you can display the t statistic this way. And so that's really everything you need to know to be able to do this problem. And so for problems 2 and 3, you have the data set, read it in just like always. Just take one of your old do files and put this data set in instead of it, and that'll be the top part of it, and leave the very bottom part the same, and then just fill in the middle with the code you need to run this problem, and you should be fine. So I will see you next time.